Let's continue and discuss thermal conversion. Thus, we need to discuss the energy required for heating and cooling. Thermal conversion is dependent on two main categories, namely sensible energy and latent energy. Sensible energy can be defined as a temperature rise without a change in state. The usual formula is Q is equal to mCp delta T, where m is in mass, Cp is a ratio of energy required, and delta T is a temperature difference. Latent energy is when a substance is changed from one state to another, for example, a liquid to a gas, without a temperature change. Energy in this case is mass times latent energy. Looking at the thermal fundamentals, ice has a latent energy content of 335 kilojoules per kilogram, where vaporization of water releases 2,257 kilojoules of kilograms. What we see here is whenever a phase change occurs, that energy is released or consumed. Next, we will discuss electrical conversions. To understand electricity, we need to understand out of what electricity consists. And this is atoms, energy, and electricity. So atom, neutral state of balance. It has a nucleus that contains a proton and a neutron, electrons in orbits, and electron energy level is proportional to the distance from the nucleus. An electron further from the nucleus has higher potential energy than an electron closer to the nucleus. Thus, it becomes less bound to the nucleus, since its potential energy is negative and inversely dependent on the distance from the nucleus. With more protons in the nucleus, the attractive force of electrons to the nucleus is stronger. Thus, the orbital energy becomes more negative. There's less energy. Orbital energy also depends on the type of orbital an electron is located in. The lower number, the closer it is to the nucleus. Here we need to remember that conventional flows from positive to negative, but electrons flow from negative to positive. Some atoms lose a positive charge, meaning they've got a shortage of electrons, and some atoms gain negative charge, meaning they've got an excess of electrons. Electric charge is measured in coulombs. Let's have a closer look at voltage. So an electrical charge can move or do work. The ability to do work or forcing the electrons to move is called potential, and this is where voltage comes in, denoted by the symbol V. The electromotive force is an electrical action produced by a non-electrical source, a device that converts other forms of energy into electrical energy, such as a battery or a generator. It provides an EMF as its output. The current and flow. This is the actual movement or the flow of electrons. We call this current, and it's denoted by the symbol I, measured in amperes. It must be moved by a potential difference, meaning voltage. It moves via a conductor. 1 amp is equal to the movement of 1 coulomb per second past a point in a conductor. Electricity can thus be termed as electric current. The current flows by moving free electrons due to the potential difference. The drift of electrons from negative to positive side of the battery, and the convention is from positive to negative. We can also thus distinguish between direct current and alternating current. With direct current, electron flow is continuously in one direction. With alternating current, electron flow changes direction by frequency in South Africa by 50 times per second, meaning 50 Hertz. Remember that the voltage in an AC circuit also periodically reverses because the current changes direction. An example of a DC piece of equipment is an LED light or a flashlight, for example. Alternating current is usually electrical motors. Here we can see the basic electrical terms and formulas, where R is resistance measured in ohms. V is voltage, it's the pushing force. I, amperage, is the resulting electron flow, and R is the resistance to flow measured in ohm. The below equations can be used mainly for single-phase power loads. Inductive loads, such as an induction motor, includes winding resistance and inductive resistance for the load. If you consider the impedance of such a load, you will get the apparent power of the load with respect to the supply voltage and current it will draw. True power tells us how much power is dissipated in heat, in which we will consider only the winding resistance. With measurements in the circuit for parameters of voltage, current, and knowing the power factor rating of the motor or inductive load, we can apply the formula for true power. For single-phase loads, power is equal to voltage times current times power factor, or cos phi. For three-phase power, power is equal to 1.73 times voltage times current times the power factor, or cos phi. Let's have a look at the power triangle, indicating the calculations for apparent power, reactive power, and true power. We will use the Pythagoras and sine, cos, and tan to calculate angles going forward. Capacitance. Usually we add capacitance to correct the power factors. Capacitors ideally only draw reactive power. They don't constantly absorb electrical energy as heaters and motors. Instead, they charge and then discharge. They bounce the energy back to the source. Capacitors supply lagging VAR required by the appliances, so the reactive power drawn from the main supply gets reduced, and the power factor of the system thus improves. Next, we look at inductance. If a coil of wire is placed in a charging magnetic field, a current will be induced in the wire. This current flows because something is producing an electric field that forces the charges around the wire. It cannot be the magnetic force since the charges are not initially moving. This something is called electromotive force. Even though it is not a force, instead, electromotive force is like a voltage provided by a battery. A changing magnetic field through a coil of wire therefore must induce an electromotive force in the coil, which in turn causes current to flow. Let's have a look at impedance. First, resistance is measured in ohms, and that is a resistance to flow of electrons. Inductance is measured in units called henries. The definition of 1 henry is simple. 1 henry is the amount of inductance necessary to induce 1 volt when the current in coil changes at a rate of 1 ampere per second. As you might guess, 1 henry is a fairly large inductor. When the alternating current goes through an impedance, a voltage drop is produced that is somewhere between 0 degrees and 90 degrees out of phase with the current. Impedance is mathematically symbolized by the letter Z and is measured in units of ohm in complex form. Energy is a capacity for action or work. Power is a rate of energy conversion. Thus, power is equal to volts times amperes in instantaneous values. Remember, RMS or real power is 0.0 0.707 times the maximum power. Let's have a look at why three-phase power exists. Three-phase power is a combination of three separate single-phase systems, basically. Power from a generator produces three separate equal voltages, each out of phase by 120 degrees phase angle. Why three-phase? It's got a lower mass of the conductors, permit more flexibility in the choice of voltages. It can be used for single-phase loads. Three-phase equipment is much smaller and lighter, therefore probably less costly. Higher efficiency than single-phase. Going back to the power triangle, let's have a look at some standard equations. The kVA, or total power, maximum demand, where Formosa spends most of its costs on electricity, is square root 3 voltage times amperage. The active, real, or useful power in kilowatts is square root 3 times volts times amps times power factor. And reactive power, kVAR, is square root 3 times volts times amps times sine theta. Next we will discuss the mechanical conversion. Mechanical conversion. Electrical is equal to mechanical is equal to thermal energy. 1 kilowatt hour is equal to 3000 kilojoules or 3.6 megajoules or 0.0036 gigajoules. The mechanical is a lifting of mass or lifting effect through rotation. So how do energy efficient appliances work? Energy efficient appliances are designed to utilize minimum energy to complete the required task. An A+ model uses as much as 20% less energy than an equivalent A-rated model, and the range of super efficient models, A++, rating uses up to 40% less energy than an equivalent A-rated model.